Welcome to the thermodynamics lecture series. So this is our Sheikh name. So today we will see the first lecture on thermodynamics, that is the introduction part 1. So coming to the contents, here we will have a contents like what is the thermodynamics and applications of thermodynamics. Then we will talk about the macroscopic and microscopic viewpoint of the thermodynamics. Then after that we will have a thermodynamic system, and then we'll have a closed system, open system, isolated system, and then finally we'll talk about the control volume. Coming to the first topic in this lecture, so that is what is thermodynamics. So thermodynamics can be defined as it is a science which deals with the energy transfer and its effects on the physical properties of the substance. So that means it will concern with the transfer of energy from one body to another body, and it will see the what is happening with this transfer and what is happening the physical properties of the substance or system. So then we will see what is the energy. Energy is nothing but ability to cause changes. So it is a simple definition of the energy. Then this thermodynamics comes from the Greek words therm and dynamis. Therm means heat and dynamis means power. So these are the two words from which the thermodynamics term is taken. Then coming to the second topic of this lecture, so that is applications of thermodynamics. So we'll have various applications of thermodynamics in various areas. These thermodynamics principles are used to find out the physical properties and the changes in the physical properties of a system. So we'll see one by one applications. So coming to the automobile engines, so in automobile engines these thermodynamics principles are used to find out the changes in physical properties and changes in something else. So then coming to the turbines, in turbines we'll have a steam turbine and gas turbines. In those areas also these thermodynamics principles are using. Then in compressor we'll have a compressor can be used in a steam power plant or gas turbine power plant, and some other application these compressors are used. In those areas also these thermodynamics principles are used. Then in pumps also, and fossil and nuclear power plants, then we'll have a propulsion systems for the aircrafts or rockets also we'll use. And then we'll have a separation and liquefaction plants. Okay, so we'll have some other applications like in refrigeration and air conditioning and heating devices also we'll use these thermodynamics principles. So these are some of the application areas where these thermodynamics principles are used. Now coming to the macroscopic and microscopic viewpoint of thermodynamics. So thermodynamics can be studied in two levels. First one is a macroscopic level, and the second one is a microscopic level. Matter can be studied in two levels. First one is a macroscopic, second one is a microscopic. So we will see one by one these things. So macroscopic level, or when we study the thermodynamics in macroscopic level, we will call it as a classical thermodynamics. So macroscopic level means, so here some quantity of matter is considered without taking what is happening inside the matter or inside a matter or the system. So that means it is not bothering what is happening what is happening with the individual particles. Okay, so we don't require any knowledge what is happening inside a matter. Then the effects which is happening in the macroscopic level, it is because of the combination of the all the molecules. So this can be perceived by the human senses, and macroscopic observations are completely independent of assumptions regarding the nature of matter. So it will not depend on the nature of the matter. Then some of the examples of macroscopic level or macroscopic thermodynamics are a moving car and a falling stone from a cliff. So when you talk about the moving car, so when car will going to strike on the wall or whatever it may be abstractly, so we will not talk about the what is happening in the crystal structure of the car body. So here we will talk about the what is the deformation, how much deformation happened on the car body. So that is we will talk about the macroscopic level, not in the microscopic level. So second example, we will have a falling stone. So when you throw a stone in the up direction, what happened? It will come back and it will strike on the earth. So when it will strike on the earth, what happened? It will split into some components. So here we will not talk about what is the crystal structure of the individual components. Here we are talking how many components it is divided, and what are the shapes of the components it is divided. So these things we will talk about in a macroscopic level, not in a microscopic level. Then coming to the microscopic viewpoint, or the microscopic thermodynamics. So this microscopic thermodynamics we will call it as a statistical thermodynamics. Okay, so here a matter, we are assuming a matter is composed of large number of small molecules and atoms. Here it requires the behavior of the individual particles. That means what is happening in a individual particle, we need to, that means individual atom or molecule, we need to study the behavior of those things. Then uh, so it will concerns with the effects of action of many molecules, and this cannot be perceived by the human senses. We can't see what are the what is happening inside in a atomic or molecular level by the human senses. Then uh, the macroscopy observations are completely depend on the assumptions regarding the nature of matter. So it will completely depends on the nature of matter. So we'll have some of the example, which is a best example, individual molecules present in the air. So if I say I want to measure a pressure of a air, so in microscopic level what we study, so in the air will have a different atoms, nitrogen, oxygen and helium, some other atoms are there. So when you want to calculate the pressure of the air, so first we need to calculate the what is the pressure of the individual atoms. So this is called the microscopic study. So this is called the microscopic thermodynamics. Okay, coming to the thermodynamic system. Thermodynamic system can be defined as a quantity of matter or a region in space upon which attention is concentrated for solving a thermodynamic problem. So a thermodynamic system may be, it may be a matter or a region. A region means there is a no matter in that region, even though we are considered that as a system. So coming to the surrounding, surrounding can be says that, so everything external to this system we are calling as a surrounding, and or will surrounding may be called as a environment also. So we'll see a right side will have a diagram where a line is separating system and surrounding. So everything external to that line we are calling as a surrounding, everything internal to that line we are calling as a system. Okay, then coming to the boundary. Boundary may be a physical or imaginary surface separating the system from the surrounding. So in the last figure we seen that a line is separating the system and surrounding. That line we are calling as a boundary. So it may be physical one or imaginary one. So the boundary may be having a property, it can be movable or it can be fixed one. Then coming to the universe, so universe can be says that, so combination of system and surrounding together we are calling that one as a universe. Okay, then coming to the thermodynamic system classification, we'll have mainly three types of systems are there. So first one is a closed system, second one is an open system, third one will have a isolated system. Coming to the closed system, in closed system mass is fixed. That means there is a no mass transfer across the system boundary. So there may be energy transfer into the system and out of the system. So at the right side we will have a figure of the closed system in which there is a no mass transfer is there, but there may be energy transfer from the system to the surroundings. Then so the volume can be changed in a closed system because the boundary is a flexible one. That means the boundary is a movable one, so volume can be changed. Then I said we'll have a best example for a closed system. A certain quantity of a fluid in a cylinder bounded by a piston constitute a closed system. So there may be no mass transfer is there, but there may be energy transfer is there. So we'll have a diagram. At the right side we'll have a container, it is closed with a lid. Here the mass is not entering into the system or leaving from the system, so the energy may be transfer from the into the system or out of the system. So this is the best example of the closed system. Then coming to the open system, in open system mass can be crosses the boundary and energy may also be crosses the boundary. So most of the engineering devices are called the open systems. So here we'll have a right side, we'll have a diagram where mass is entering and mass is leaving. So that means mass is transferring from the surrounding to the system to the surrounding. And here we'll have energy in, energy out. So that means energy is transferring from the system to the surrounding. Okay, then in open system we'll have a best example, an air compressor in which air enters at a low pressure and leaves at a high pressure, and there are energy transfer across the system boundary. So that means when in a compressor where entering air which is having a low pressure, after leaving it will gain the energy there in terms of pressure and it leaves the surroundings. So that means mass is coming in, mass is leaving, and it is also gaining energy. So that's why it is called the open system. So at the right side we'll have a simple diagram where it will indicates the open system. So same container, but here lid is removed. So that means we can pour a sugar or we can pour a coffee also, or because when you heat this container, the vapor will form and it will be leaves the container also. So when you compose that container as system or that water as a system, so it is mass is transferring and energy also transferring when you convert it into vapor. So this is the best example of the open system. Then coming to the isolated system. So in isolated system there is no interaction between the system and surrounding. So there will completely isolation is there. Then there may be a fixed mass and fixed energy is there. There is a, that means there is a no mass transfer, there is a no energy transfer across the system boundary. So these type of systems we call it as a isolated system. So at the right side we will have a diagram where it will indicates a isolated system in which there is a no mass transfer, no energy transfer. That means it is living as a isolated one. Then so this is the best example of isolated system. But if, so whatever it may be, isolation, complete isolation, pure isolation will not exist. So some energy may be losing from the system, but pure isolation it is not there. So this is a flask where we don't have any matter transfer, that is no mass transfer is there and there is a no energy transfer is there. So that means in the flask we'll have a hot water or a hot tea. So hot, when you close the lid of the flask, so the tea will not come out. So that means there is no matter transfer or mass transfer. So the flask when you open after 1 hour 2 hours also, the hotness of the tea will be remain there. So that means there is a no heat transfer from the system to the surrounding, we are assuming. So complete some losses are there, but you are not taking those losses into consideration. So these are about the isolated system. So these are the some of the thermodynamic systems we will have. So last topic on this lecture is control volume. So control volume can be defined as a for thermodynamic analysis of an open system. So this is an open system, but here such as an example is an air compressor. Attention is focused on a certain volume in a space surrounding the compressor. Here a certain volume in a space is considered around the compressor and is known as the control volume, and it is bounded by a surface, it is called the control surface. So here matter and energy can be crosses the control surface. Then this is a simple diagram where we will have air compressor and a dashed line is there around the air compressor, which is called the control surface. And air is entering into the system and leaving out of the system. So that means mass is transferring and work is done by the motor onto the system and heat is leaving the system. So that means energy is transferring from the system to surrounding to the system. So that means energy transfer is there. Okay, so this is a control volume, also a open system. Okay, but there is a main difference between the open system and control volume is apart from the open system, in control volume the mass flow rate in and out of the system is constant. So definitely mass flow rate need to be constant in the control volume at the inlet and outlet condition. But in open system the mass flow rate is not constant value. So this is our end of today's lecture. Thank you. So this is your Sheikh 9 signing off.